The Elements of Non-Euclidean Geometry by D.M.Y. Sommerville.
Chapter 2, Elementary Hyperbolic Geometry. Section 24, Geometry of a Bundle of Lines and Planes. In plane geometry, we have points, lines, distances, and angles. In a bundle of lines and planes through a point O, we have lines, planes, plane angles, and dihedral angles. Let us change the language to make it resemble the language of plane geometry. In translating from one language to another, we require a dictionary. The following will suffice. Define point as a line through O. Define line as a plane through O. Define distance between 2 points as the angle between 2 lines through O. Define angle between 2 lines as the dihedral angle between 2 planes through O. Define parallel lines as parallel planes. Then 2 points determine a line and 2 lines determine a point. Parallel lines only exist when O is at infinity or ideal. When O is at infinity, through a given point, there passes just one line, parallel to a given line, section 19. And when O is ideal, 2 parallels can be drawn through a given point to a given line. There are therefore 3 kinds of geometry of a bundle, according as the vertex O is actual at infinity or ideal, and these are exactly of the same form as elliptic, parabolic, i.e. Euclidean, and hyperbolic plane geometry. If a sphere be drawn with a center O, cutting the lines and planes of the bundle, we can get a further correspondence. When O is an actual point, we have a proper sphere. We have the following dictionary. Define point as a pair of antipodal points on a sphere. Define line as a great circle. Define distance as the length of arc. Define angle between lines as angle between great circles. Hence the geometry on a proper sphere, where great circles represent lines and pairs of antipodal points represent points, is the same as elliptic geometry. See further Chapter 3. When O is ideal, the sphere becomes an equidistant surface, and its geometry is hyperbolic. When O is at infinity, it becomes a horosphere, and its geometry is Euclidean. Point in each case being represented by a point, and lines by normal sections, which are also shortest lines or geodesics on the surface. We have here the important and remarkable theorem that the geometry on the horosphere is Euclidean.
The Elements of Non-Euclidean Geometry. This book was written by D.M.Y. Sommerville, M.A. and Doctor of Science. It was published by the Open Court Publishing Company, London, G. Bell & Sons, Ltd. in 1919, and now is in the public domain. It is being read by Jim Renholt, with programming and illustrations by Jim Renholt in 2019. Thank you for listening.